Hello.
So I have no idea what's going on with Canvas. It like randomly changed the code number.
Oh.
After I had created the class and sent out the links, it looks like it randomly like reinvented the code number. I have no idea what's going on.
Yeah, thanks. I'm here. I got your no announcement you sent, so I'm here.
Yeah, no, it's like I'm trying to, I like posted a couple of different announcements and then I did a cut and paste or a copy paste and tried to try this one because I'm so frustrated.
Yeah.
I hate Zoom so much.
Yeah. The last one you sent, try this one you sent, it actually worked.
Okay. It looks like after giving me the same code for like all the meetings that I had scheduled previously, it's like it suddenly changed the number.
Wow.
I'm not really entirely sure what the deal is. Arg. So yeah, well, hopefully I can get most people logged in here in the next few minutes. It's like something about the last or the last 4 digits of the code or whatever are different, which actually is not the way it was last semester. Last semester, it gave me the same number for like the meeting code, no matter when I scheduled it. So I'm not really sure what the deal is.
Yeah, because I thought the meeting code was based on the host, not the time. At least that's how it seemed to function for Ippolito.
There's massive crashing going on upstairs.
Oh, that's what we're dropping. But yeah, because Ippolito used the same meeting code for both his lecture before the lab that I was in and the lab itself.
Yeah, so yeah, I'm utterly frustrated. I don't know. First rule of Zoom, if anything can go wrong, it will go wrong. So while I'm waiting for other people to log in, hopefully, for lab tomorrow, I have on my list Faustin, Galovix, Lee, Morin, Stengel, and Turner. That should be my group B people.
Yeah. I have a question. I'm on the group B for tomorrow. And I've noticed the homework for the lecture is due tonight.
Yes.
Would you mind if I bring the homework, like, because I'm doing it on paper? Do you mind if I bring it to lab tomorrow, or just send it to you tonight by email?
I don't have lecture rigged for inputting non-digital grades the way I do for lab.
Oh.
So it would be better if you send it to me electronically.
Okay.
All right, let me talk about lab tomorrow night, just because I think this applies to a few of you. So I found out weirdly on Friday that the bookstore, at least on the beach campus, keeps utterly ridiculous hours, which finally clued me in as to the fact that people have been having problems getting the lab book. So let me see if I can do my share screen and okay, I guess I don't have that popped open. Hang on for a second. I loaded a bunch of stuff so that hopefully you can see it from the shell for Canvas. Okay, let's try to do my share again. All right, so this will be the way the shell looks like when you're loaded in for lab. So dry lab 1, okay, if you click on that, there are multiple pages here, okay? Specifically, you need to print out, if you do not have a lab book, the one here that says dry lab extra exercises. It's, I mean, if you had a lab book, it's a back and a front, okay? If you don't have a lab book and you're printing it, it's 2 pages. So you need that when you come to lab. If I go back over here to pages again. Okay, I also then down here where it says experiment 1, this one also, I think, should have the pages that you need for experiment 1. Let me see if it'll let me view this. Yeah, so it looks like this. Okay, it says experiment 1, basic lab ops. Okay, and if you like continue to scroll down, because it says here page 1 of 4. Okay, so there's those pages. Did it not? I'm trying to figure out if it didn't load the report page for that. Hang on, let me go back over here to modules and see if I... Nope, that one doesn't have that. Okay, that one doesn't look like it has... Somebody else made the PDFs for me because I don't have a PDF generator. Because that one says report sheet. Okay, so that's all loaded. Okay, and then back over to this. Okay. And then that one, oh, that's actually just looks like 2 versions of the same thing. This doesn't look like it has all of the pages for experiment 1. It's like it's got the instructional pages, and it's supposed to have a report page that says report sheet, lab report sheet at the bottom. Hang on, let me see if I have access to... I'm trying to see if I can reload the report page for the other one, because I know that there's probably still some people who may not have access to... All right, so that, edit. Okay. I don't know if I actually have a digital copy of that. because I thought it had all of the pages loaded, and actually it looks like it doesn't. All right, I don't have a digital version of that. All right, I am utterly frustrated. All right, how many people who are supposed to come to lab tomorrow still don't have a lab book?
I don't have one.
Okay, so like I said, I found a digital version of the dry lab extra exercises. I'll have to see if I can make some photocopies for the actual report page, because I don't have, yeah, apparently it's not part of the file. It should have been a 6-page file. And when it was scanned, it looks like there's only 4 pages in the file. Because like I said, I don't have all I have is a standard Acrobat reader. Okay. I don't have the ability to create a PDF file from the lab book. I guess I will try to bring some extra copies of the report page with me tomorrow, because that seems to be a still ongoing problem. I know that the Beach Campus bookstore has ridiculous hours. I found this out because I was trying to buy my daughter's textbook for the class that she's taking. And like Monday through Thursday, they're only open till 3 o'clock. I don't know if the MacArthur Mall part of the bookstore, I would assume it's open later, but I'm not sure about that. Print what you have, print what I've already loaded so that you at least have all the other pages. The dry lab stuff, the stuff that's just extra exercises, that you definitely need in lab tomorrow. And you should probably have the instructional pages for experiment 1. I just don't have a file apparently that is for the lab report itself. So bring what you can, and I will see what I can scour up in terms of report pages. But next week when we go back to actually having lab twice a week for A group and B group, everybody really needs to have a lab book by then, because I don't have any other scans for that. So we're trying to make do for this week, but yeah, definitely need to get a lab book for next week.
Miss Mollers is Lewis Jackson. How you doing today, ma'am?
Yeah, hello. Sorry about the disaster of the whole Zoom thing. They changed my numbers.
No, it's no problem. This is my first day in the class, and I was never assigned a group, so I was just wondering which one you'd like me to. I guess there were less people already, or more people.
Oh, do I have 8? Because I had, I think, a 7 group and an 8 group, because I had 15 people registered. Let me look in my announcement section. Yeah, come tomorrow if you can, since I have 7 people registered for my B group, and I already have 8 people in my A group. So if you can, come tomorrow. Will that work? Will that work for group B? For group B?
Yes, ma'am. Sorry, I lost connection. That'll work.
Okay.
Sorry.
So yeah, I have 8 people already in the group that I lumped together for part A, for group A. So if you are available tomorrow, then show up as part of group B.
Yes, ma'am. We'll do.
Okay.
I have a quick question.
Yes.
So I went to the beach campus to try to get my lab book, but it was closed. But does the beach campus have the Norfolk one, or should I just get it?
I would recommend calling them.
Okay.
I don't know whether they have Norfolk lab books on that campus or
Okay.
not.
Okay,
You
sounds
know,
good.
I think I would give them a phone call, because I'm not
They
sure.
don't have it.
They don't have it.
Yeah, they don't have it.
Okay. Okay. Thank you.
Okay, so yeah, in that case, it sounds like maybe you have to go to the MacArthur one.
Okay, sounds good.
Hey, I have a quick question. I'm sorry if you answered this last week.
Mhm.
If you go to the Zoom invitation link under the pages through Canvas for your course, it says that we do every 2 weeks the Zoom meetings.
No, that's
Okay, I figured it was
not
wrong because we're
true.
obviously here.
I don't know why it.
Yeah, it
Yeah,
says we meet 11 times and
I've
then
had a
it has alternating.
never-ending set of problems for some reason after having minimal problems with Zoom for the spring. I have had nothing but problems so far this summer.
Yeah.
So I think what I'm going to have to do is each day I'm going to have to do a cut and copy paste into the announcement section because it looks like
But I think what your problem may be is that one link that worked last week, it may only work for the weeks that you have in the Zoom invitation link, if that makes sense.
okay.
Is you have it for like the 25th and 27th, which was last week, and then it goes for the 8th and the 10th and the 22nd, the 24th. So it just skips a week, you know? So I feel like that link will probably work every other week, as painful
Yeah,
as that sounds.
I'm gonna try to make announcements so that you can just check the announcement section each lecture period because yeah, it was supposed to give me 20 lecture meetings, 10 weeks times 12 a
Right.
week. And it didn't, and I don't know why.
Yeah. All right. It's no big deal. That was just my
Yeah, I
question.
clicked the
I was
box
just wanted to
that said
clarify that.
Tuesday and Thursday, but yeah, I don't know what happened.
All right. No big deal.
I hate Zoom so much.
And I have a question to you, Professor.
Uh-huh.
The homework I submitted it. Is it just taking time for it to be graded, or is this?
Oh, no, see, I won't start grading them until tomorrow morning
Oh, okay.
because since the due date is midnight, I won't even open them and look at them until tomorrow morning.
Okay.
Yeah, I usually sit down and try to do a mass grading the morning after homework is due, because that way I just kind of sit down and crunch through it all at one time. I don't necessarily grade them as they're submitted. So yeah, if you turned it in the past couple of days, I see that it's there, but I haven't looked at them yet. Because tomorrow, after the deadline shuts down tonight at midnight, then tomorrow I will post the answer key so that people can have a look at it before we go over it on Thursday. So that way I kind of like, it kind of a back and forth thing. But yeah, I haven't looked at them yet. Other questions regarding homework? Like I said, you can scan it if you have a flatbed scanner. Most of the smartphones these days, you can download an app where you can take the picture and tell it, make it into a PDF, and then port it across. Or because it's a Word document, you can literally just type your answers into the document and save it again with your last name at the end and submit it that way. So that you have a couple of different options for how you could sub it.
Cool. Thank you.
All right, other tech questions, because all of this has been kind of a snarl today. All right, we are going to head onward. I'm gonna probably do about 10 or 15 minutes worth of chapter 2 stuff, give you guys a little break, and then kind of keep on going with chapter 2. This, I went back and re-edited my chapter 2 file. It has a couple of additional pictures in it, and you may want to re-download it at some point if you like. All right, some of the things that are in this particular file are actually not in your lab book or not in your textbook. Some of it is supplementary information that kind of goes with the topics to hopefully give you a little bit more background and clarity on some of the history of chemistry, as well as some of the topics we are heading into. So we looked a little bit at the periodic table over the past couple of weeks. If you look at the one that I loaded to Canvas, you will see that there are 118 boxes these days. Some of them have temporary names because officially designating a new element is a very lengthy and somewhat political, not political in terms of governments, but political in terms of universities, way of deciding who gets to name it. Of those 118, all of those that are above 100 are things that are recent creations. They are all radioactive and have these teeny tiny little half-lives that might be anywhere from half a second down to nanoseconds. Of the ones that occur before 100, though, 88 of them are actually naturally occurring. So even before we hit number 100, some of the ones that were in there are not found in nature, in particular TC, which is technetium. So one of the things that you need to kind of begin to get a handle on, and this is sort of different for better and for worse than a face-to-face class, is you need to have familiarity, okay? Because since this is a digital class, normally I tell people, buy a pack of file cards, number them 1 to 100, put the name on one side, put the symbols on the other side, and just brute force memorize them, okay? Which actually has a certain advantage because making yourself memorize them gives you a kind of like fingertip availability in terms of what those names are supposed to be. Obviously, since we are doing this in a more digital fashion, you don't have to memorize them. However, you should be really, really familiar with them, because not only are you going to begin to see them utilized here in this chapter, then they will continue onward as the semester progresses. There are 6 elements in particular that have relatively critical importance to humans, especially being that we are living systems. Sometimes you will see the, I'll call it an acronym of CHOMPS, CHONPS, as the 6 most common elements that are in a living system. And so I gave you a little list here of the ones that fit those particular symbols. Carbon, we are carbon-based life forms. Hydrogen, oxygen, nitrogen. And then we also need a little phosphorus and sulfur so that such things as proteins and ATP and some other important molecules can be created. So we are going to backtrack a little bit. Back to, Golden Age of Greece, which is about 500 BC. And 2 important dudes back then, famous dead guys, Democritus and Leucippus. And way back then, science and philosophy were actually not 2 different things. They were kind of this tangled together overlap of the 2 items. Well, they were scientists / philosophers of their time, and they came up with a term that we continue to hang on to most of the letters of. And they decided that everything in the universe was made of these small, indivisible meaning can't be cut apart, particles. and they called them atomos. Okay. Obviously, we dropped the second O at a later point in time and shortened it up a little bit then to refer to them as atoms. Okay, great, fabulous idea. No tech. Okay, so they have a hypothesis, no experimental data to actually support their hypothesis because no tech. So we're going to jump ahead to about the 17th century, so 1600s. In this time period, you have something that actually is a little more akin to alchemy. And also think about the fact that during that time period in the 1600s, okay, probably less than 2% of the population could read or write at all. Therefore, the people who were the scientists of their day were the very few educated people, and they tended to read and write Greek and Latin, and then as we head into the sort of the end of the 1600s and on into the 1700s, throw a little Latin in. Okay, if you're an alchemist, your big goal in life is let's turn lead into gold. Okay, and you end up with a kind of it's almost kind of a religion in a weird and twisted way. It's got some mystical components to it, but they also had a little bit of data. There were a few experiments that were being run back then because they had balances and they had a few other things they could use, glassware, but definitely limited. So we have done the impossible. If you have a few terawatts of electricity and a handy nuclear accelerator, you can actually turn lead into gold. And it's been done. The last experiment that did this made, I believe, 11 atoms. So you wouldn't exactly call this a cost-effective method. So let's segue back to the whole Greek and Latin idea. So one of the things you may have noticed if you've begun to look at the periodic table is that some of the names that we use and some of the symbols that we use don't appear to match. And this harkens back to the Latin. So I found a nice, cute little graphic here to give you some of the more common ones. So antimony used to be known by the Latin name of stybium. We kept the S and the B part of that. Copper was known as cuprum. We kept the C and the U. Gold was aurum. We kept the A and the U. Iron was ferrum, so kept the F and the E. Lead was plumum. And if you know a little bit about the fall of the Roman Empire, the fact that Romans actually had indoor plumbing, but the fact their plumbing was made with lead pipes. Think about that for a moment. You have all these people who are drinking water that has flowed through lead pipes. So let us say this was probably a contributing factor to the fall of the Roman Empire because everybody was getting lead poisoned. Mercury, once upon a time, was hydrogyrum. If you work in medicine, potassium and sodium, you may have noticed, are the K and the Na from kalium and natrium. Silver was argentum, tin was stannum, and here's where the German comes into play. Tungsten was the German word wolfram, which is why tungsten keeps the W as its elemental symbol. Like I said, because we're doing this digitally, you don't have to commit them to memory. However, I will tell you that the more familiar you are with the name and symbol combination, the easier you will find it as we progress, not only through this chapter, but through the remainder of the semester. All right, let's hop a little bit more in time. This time we're going to do mid 1600s. Mid 1600s, we hit a guy named Robert Boyle. Okay, and one of the things that he did was he began to study the fact that air had a pressure and volume relationship. So later on down the line, when we get to the gas laws chapter, we are going to name one of the gas laws after him. So more famous dead guys. Jump a little bit further. Now we're into the mid 1700s, and we get Mr. Pyro. Okay, the guy who liked to set stuff on fire. His name was Antoine Lavoisier. He was French. He liked to burn things, but he also kept a lot of really meticulous, detailed notes, and he began to figure out what is known as the law of conservation of mass, also sometimes known as the law of conservation of matter. You will find out that if you sort of paraphrase what he came up with for the law, matter is neither created nor destroyed, only rearranged. You can also say it as, you don't get to make it or break it, you only get to rearrange it. And this is true for all standard versions of chemistry, nuclear chemistry notwithstanding. All right, Joseph Proust. He has a different take on things. He is one of the ones who helped figure out that if you're looking at particular compounds, they have ratios, okay? Back to water, okay? H2O. One of the things that he realized was if it was a water molecule, you had to have twice as many H's as you had O's. So this one gets a rule called the law of definite proportions. Proportions sort of relating to the idea of ratios and or fractions. So now we're going to jump from France back to England and John Dalton. John Dalton was a bit of a thief in that he stole ideas from a whole bunch of his predecessors and expounded upon them a little bit more. I should say maybe say expanded upon them a little bit more. And then he wrote a paper, and in the world of science in general, the people who publish the paper are the ones who get credit. So he gets credit for a lot of things that aren't really actually his idea. He took the ideas of Proust and he kind of ran with it a little bit and decided that if you took two elements, sometimes you could combine them in different ways. So let me go back over here and switch over to my whiteboard for a second. All right, so hydrogen and oxygen, we have two options, okay? We've got H2O, okay, water. You can take the same elements and make a different molecule that though it is good for disinfecting the cuts on your skin, you would not benefit from drinking hydrogen peroxide, which is the H2O2 molecule. Same elements, different ratio. So ratios and proportions make a difference. So his statement there, you can go later, go back and read his thing he calls the law of multiple proportions. This also will tie in later to another related topic that we will get around to, known as empirical formulas. So all of this sort of gets introduced a little bit in this chapter, and then you don't really see much of it again until a little bit later. So like I said, he wrote a paper. He stole from Leucippus, he stole from Proust, he stole from Lavoisier, and he kind of put them all together and wrote a paper about it. So the first one is the Leucippus and Democritus idea of each element is made of particles called atoms. Yeah, no, he didn't hang on to the Latin name. He did use the unlatinized version and call them atoms. He then used some information from some other people, as well as a little bit of his own data. And note it says atoms of a given element are identical. Atoms of different elements are different, which from our modern 21st century point of view kind of sounds like a duh moment. But remember, he has a little bit of technology and a little bit of equipment, but not the kind of instrumentation that we have available now, like gas chromatography and mass spectroscopy. So pulling some of this data together did take a bit of doing. If you stick them together and they make compounds, the relative numbers are important. And then back to the stealing from Lavoisier again of chemical reactions are reorganizations. You don't get to make it or break it. All you get to do is rearrange it. He did some good things, though, in that he began to organize the data that had been amassed by some of these previous people. And he began to construct periodic tables, which only bear some resemblance to the current one, because he didn't use atomic numbers the way the current table is arranged. He used atomic masses. So we have since elaborated, added additional elements, and kind of reorganized since his original attempts at this. So now we're getting closer to modern day. We know that elements are made of atoms. If you stick the atoms together, you get compounds. But up until the late 1800s, they hadn't really given a lot of thought to what if atoms aren't the smallest thing? What if there's actually stuff that's smaller? Okay. So in the 1890s, J.J. Thomson, aka Lord Kelvin, the one who got a temperature scale named after him, was studying cathode ray tubes. These are primitive, old school, kind of like really like 1960s, 1970s TVs. Okay, no flat screens, the kind that were really deep and took up lots and lots of space. And I found a picture I liked. Okay. These are cathode ray tubes. They literally look like tubes, okay? They are plugged in at one end, and they have electricity flowing through them. So he analyzed his data a couple of different ways. If you look at the first left-hand one there, You just see the straight line. Okay, it has kind of a green stripe that goes across the length of the tube. That was kind of his first run. So then he decided, well, is the stuff that makes the stripe an actual item, like a physical thing, or is it more like a light beam? So he hung something in its way. And you see the little funny kind of crossish shaped thing that's hanging there. And he hung it in the way inside the little test tube there. And he found out that no, in fact, it is a little bit like a light beam in that there's a shadow. When that little green stripe hits the little cross-shaped item, stuff doesn't go through it. So you get a shadow behind it. Then look at the one on the bottom of the left-hand column. And you might have to go later back and kind of expand this and blow this up a little bit. But where it says charged metal plates, the top one is negative and the bottom one is positive. Note the green stripe bends toward the positive one. More data. He's beginning to discover that not only is that little stripe made of little somethings, okay, those little somethings must be negative. So then he decided he would try a magnet, because magnets influence charges. And he found that the magnet bent the little green stripe. So the last thing that he did, because he still wasn't sure if it was more like a ray of light or if it really was an item, basically a tiny chunk of something, is he put this little paddle wheel inside the tube and sealed it all back up, fired it up, and the paddle wheel turned. Therefore, what he was proving at that point was that these little tiny chunks of something were not only chunks, they were negative chunks, and they had some kind of actual physical existence. Okay. He also knew that because atoms were not negative, that there must be some positive bits in there somewhere, okay? And being a British dude, I spelled this wrong. I left out one of my letters of the alphabet here. He dubbed this the plum pudding theory, okay? If you do not know what a plum pudding theory or a plum pudding is, think fruit cake you set on fire, okay? That's actually what a British plum pudding is. You have all this candied fruitcake stuff that's all jumbled in there without any sort of organization, and you douse it in whiskey and you set it on fire, and then in my opinion, you throw it in the trash, because I think plum pudding is gross. But look at his picture, okay? He was at least heading in the right direction by understanding that there must have been negative bits and positive bits in order to make this work. Otherwise, everything would stick together. Okay, so he's beginning to sort of grasp that there have to be these different parts to it. All right, so let's take about a 10-minute break, and then we will come back and talk some more about the evolution of what we know now about what the atoms actually look like. So we're heading in that direction. Some of these pictures are also in your textbook, but not all of them. So that's why I added some additional pictures into the file for the notes. So we'll be back in about 10 minutes and continue on with this. And I'm gonna flop back over to Canvas and see if anybody else sent me email. One of the downsides of like being at home for lecturing is then it's like I have to have, or I am required to have input on the cooking of the dinner. So I had to go have a conversation with my husband about if he had picked up something from the grocery store and all those fun things. So while I'm thinking about it, before I get back into chapter 2 stuff, I did manage to get the first lecture from the 25th, I think it was, crunch through YouTube. I hope the link works. That was a monumental, because it's such a big file, because it's like an hour and 40 minutes worth of video, trying to get that downloaded and then loaded across to YouTube so that YouTube can crunch it. So I hope, I haven't checked the video file. I haven't like poked my way through it to make sure the integrity is okay, but it's there. That one I've got loaded up. If you need to go back and have a look at it, I'm gonna try to do the one from last Thursday, maybe tomorrow. So we'll see how that works. It's just trying to load this across is really a problem.
What name is it under?
As far as the YouTube thing,
Yes.
I mean, it should be under my name, but I just copy pasted the link.
Okay.
I mean, it's like, yeah, I have a YouTube channel, but I created the YouTube channel so that I could post lectures. Although I will say there's also some lab stuff on there too. If you go and you look at the chat at the channel that's under my name, there's lab videos under there too, as well as a couple of book videos, since that's my other job. Since I write romance books, there's a couple of promotional videos also loaded on the channel too, so that have nothing to do with chemistry. But yeah, I just did the click on the link thing and did a copy paste for that. So hopefully the one that I did that for the summer is now viewable. All right, back to chemistry history. All right, the plum pudding theory did not stick around for all that long. Millikan, who was a buddy of Thompson's, came up with a way to figure out how much or how big the negative charge was on the electron. And then things kind of thumb twiddled for about another 10 years until Rutherford came along. So Ernest Rutherford was studying radioactivity, and he had a bunch of premises that he was trying to prove was true. And he took a radioactive element and he put it in a little lead block. He drilled a hole in it so that the alpha particles, which are something that is emitted by radioactive elements, well, some radioactive elements, would only come out in one spot. And he aimed it at a detector that had a little piece of gold foil in the center. And because at that point in time, he thought that J.J. Thomson was on the right track, what he expected was that when he fired these little alpha particles through that piece of gold foil, that you would mostly only get little blips of light over on the opposite side behind the gold foil and not really anywhere else. Okay, so he fired it up, he got it going, and look at where the arrows go. Okay, some of the arrows went through, some of the arrows bounced at 20, 30, 40 degrees. Some of them bounced almost straight back. Okay, and he was a compatriot of J.J. Thomson, and he actually wrote the guy a letter because, of course, pre-internet and all that. And he said it was like firing a cannonball at a sheet of paper and having it bounce back. Okay. He indirectly, unwittingly proved that this whole concept of the atom just being this wad of positive and negative charges all just sort of lumped together was wrong. And so you end up with something that is more akin to the things that we look at currently, where it has a center and a middle and edges. And I realized I meant to put another picture in here. Hang on, let me grab my binder. Oh, phooey. It's going to take me a minute to see if I can find the picture that I am looking for. Because I dumped it in another folder. And yeah, can I actually find it? This is the question. And no, I have no idea where I put it. All right, now I'm doubly frustrated. All right, can I do this? Can I share? All right. Not a great way to do it, but it kind of works. So look at the picture there. We've got Dalton's version, which is basically it's little and round. Okay. We have Thompson's version, which, okay, chuck the positives and negatives in there together, and that's kind of it. Then we hit Rutherford, which has a nucleus in the middle. And we are heading in the direction of Bohr, which makes it look like a little solar system. And eventually we will talk about the infamous Mr. Schrodinger and the quantum theory version of atomic theory. So you get this sort of evolution of where all of these things are sort of coming from. The nucleus, dense, small, in the middle, kind of like the sun in our solar system. And if we start looking at it in terms of how big is it? Okay. A nucleus is about 10 to the negative 13th centimeters. Then we also know it contains protons that are positive and neutrons that have no charge. And the electrons, the negative parts discovered by Thomson, are about 10 to the negative 8th centimeters away. Look at those two exponents. We have one exponent that says 10 to the negative 13th. We have another exponent that says 10 to the negative 8th. That's 5 zeros, okay? So I found a good rationale on how this sort of works out. If you blew up your nucleus so that it was roughly the size of an average grape, the nearest electron would be about a mile away. So there is a fabulous bumper sticker that I have seen that says, "Be humble. You are 80% water, and the rest is empty space between electrons," which is really kind of true. If we look at this on a little bit more numerical level, neutrons and protons are approximately the same size, and they are both about 1,839 times the weight of an electron. If you look at page 79, there's a little bit of additional information here. You will see that there is a small difference, okay? The protons are 1.67262, whereas the neutrons are a little bit heavier, 1.6493. Both of those are to the negative 24th power. Okay. Why is the neutron heavier? Okay, here's a little hint that comes from the nuclear chemistry chapter, which actually is a second semester topic. Because a neutron is in actuality a proton and an electron glued together with a neutrino. Okay, so digging a little bit deeper into quantum theory. But if we stick to the basics, everything in matter is made of protons, neutrons, and electrons. Well, how do we get 118 different elements? How many of each do you have? If we start at the very bottom end, okay, this is the upper left-hand corner of the periodic table. Hydrogen is the very first element. Hydrogen has one lonely little proton and a single electron and nothing else. There are no neutrons in an average hydrogen atom. All bets are off if we talk about deuterium. If you look at each of those little boxes on the periodic table, you will see that there are some additional numbers, and they tell you different things. And so I picked on iron, okay? So the whole number is your atomic number, which in the case of iron is 26. It also means that you have 26 protons. And if we're talking about neutral atoms, that also means you have 26 electrons. Look at the decimal number. The decimal number, 55.845, is a combination of protons and neutrons. But then that kind of gives you the head scratching of, well, if we subtract, if we do 55.84, whatever, minus 26, that gives you a decimal. It gives you 0.8 or so of a neutron. You can't really reliably have a part of a neutron. So what does this actually mean? All of those atomic masses are based upon the idea that in nature, each element has more than one isotope. Isotope is a word that people kind of reflexively go, oh, you must mean radioactivity. No, actually not necessarily. An isotope means you have an element with the same number of protons, but you may have different numbers of neutrons. Makes it the same element, just different versions of the same element. These are also tied into the idea of AMUs. AMUs are a unit, literally atomic mass unit. 1/12 of the weight of a carbon-12 atom. You will see that my capital letter C that's written there has a 12 kind of written above and a little bit to the left. This is known as isotopic notation, and it is a way to help figure out that you have different versions of the same element. Well, if you have multiple isotopes, not all of them are equally popular, okay? If you go to one of the big office buildings around here and you look in their parking lot, and you will see that these days there's a lot of little SUVs and some pickup trucks and probably a very small handful of motorcycles. Obviously, they have kind of a different ratio. If I pick on magnesium, magnesium actually comes in 3 different isotopes. There's the really popular version, which has a percent abundance, that's how often you can find it, of 78.7. So that's isotope number 24 for magnesium. There's a slightly heavier version of magnesium, which has 1 more neutron. Therefore, it has a mass of 25. And then there is 1 additional version of magnesium that has yet another neutron. So it has an atomic mass of 26. Now note, isotope 25 and isotope 26 of magnesium are less popular. They have percent abundances that are quite a bit less. If I take my isotope mass and I multiply it times my percentage while I am moving the decimal place. So 24 times 0.787, 25 times 0.1018, and 26 times 0.1117. You will get the numbers that are here on the right-hand side of the equals. You get 18.88 for the most popular one. You get 2.53 for the magnesium 25. You get 2.90 for the magnesium 26. Now, one of the things that is true about this, and this is referred to as a weighted average, there is no division step in a weighted average. This is how I do grades, okay? At the end of the semester, I will take your test average and multiply it by 45%. I will take your homework average and multiply it by 13%. I will take your discussion average and multiply it by 2%. And once I get all of those together, then I will total them. Actually, Canvas will total them for me because it's a spreadsheet. And that will calculate your numerical grade. Okay, so this is actually how many things are done. In this particular case, we are applying it to various isotopes of elements. The other thing that ties into this is if you are given a particular isotope, you should be able to determine how many protons, how many neutrons, and how many electrons. So if I pick on carbon 14, the radioactive version of carbon, if you look up carbon on the periodic table, it's atomic number 6. And unfortunately, Microsoft Word is not super cooperative about being able to allow me to write a number as an upscript and a number as a subscript at the same time. So I did not insert the subscripts. You need to refer to the periodic table to look those up. This will tell me that I have 6 protons and 6 electrons, and I must subtract to figure out how many neutrons. That top number, the number of the isotope, is not the answer by itself to any of those 3 particles. You must subtract. So 14 minus 6 will give you 8 neutrons. For gallium, gallium's a little bit bigger element. Gallium is number 31 on the periodic table. If I figure out my particle numbers, I have 31 protons and 31 electrons, because at the moment, we are making an assumption that our positive bits must equal our negative bits. And then do 70 minus 31 to determine that you have 39 neutrons. Now, since we mentioned AMUs, and I guess it's because carbon is important to living systems, I don't know if there's a hard and fast reason other than that as to why it's picked as the basis for an AMU. One carbon-12 atom is said to be 12 atomic mass units. Like I said, I'm not really sure any reason other than it's important to living systems. We could also translate this into grams. 1 AMU is a really small number of grams. So if you have 1 carbon-12 atom, which weighs 12 AMUs, if you weigh the carbon atom and you have 1.99 times 10 to the negative 23rd, divide that number by 12, and you get an even smaller number, which is the weight of 1 AMU. So 1.66 times 10 to the negative 24th. And yes, in our current 21st century technology, we do actually have instrumentation which allows us to see atoms. We have atomic force microscopes, and we have scanning tunneling microscopes. If you go on YouTube and you input into the search bar an atom and his boy, there is a little 1.5-minute long video that was created by IBM, using an atomic force microscope, and they created a stop motion video that uses silicon atoms, individual silicon atoms, to create a little video. It's really kind of a fascinating little video. Like I said, it only lasts about a minute and a half. And you might want to go have a look at that at some point. It kind of gives you an idea, just sort of how high tech certain things have become. Since I am old, okay, one of the things that I remember from high school chemistry is discussions about like, oh, we're never ever going to actually be able to see the atoms, so therefore we have to all use indirect evidence to determine this. Well, that's obviously changed. All right. Now we're going to kind of jump from talking about individual atoms and their particles for a few minutes, heading in the direction of sticking them together. So one of the things we said in chapter 1 is that a molecule, the smallest part of a compound, is usually made of 2 or more atoms that are stuck together. And so you can write out a chemical formula, and there are some rules that guide this. But to give you kind of a basis for this, take a look at these 2 molecules. We have MgSO4. Okay, so using a periodic table and the subscripts, we can determine what atoms are within that molecule, which is known as magnesium sulfate. So the capital M little g is the chemical symbol for magnesium. And kind of like algebra, there is no number to indicate the fact that you only have 1 atom of magnesium. You also have a single atom of sulfur, capital letter S. But you have 4 atoms of oxygen. Look at my other molecule. Okay, this one has some parentheses in it. Again, we're going to kind of use algebra rules here. Since there's a little 3 outside the parentheses containing the NH4, this molecule actually has 3 nitrogens, 12 hydrogens, because little 4 times little 3, 1 phosphorus atom, and then 4 oxygens. Now, structural formulas are a little different, and this is something that I need to draw to kind of show you how this works. All right, so first we're going to start with the name of it. We're going to call it acetic acid. This is a molecule you will see frequently during the course of the semester. So one way you can write it is H, and I can't do my subscripts easily, but HC2H3O2, okay, with the numbers being actually subscripts. So that's one option. Here's another option, CH3COOH. This begins to give you a little bit of a clue on how the molecule is built. So now let me do the drawing thing. All right, this molecule has a C on one end that has 3 spokes that are hydrogen atoms. Then the second atom of carbon is next door. The first atom of oxygen is double bonded to that carbon, there is another O. And dangling out here on the far right-hand end, I have a final hydrogen. All of these three versions are acetic acid, including the word, okay? But the final version gives you an indication how the molecule is assembled. We're only going to pay a little bit of attention to the assembly version of this, the structural formulas, here early in the semester. However, toward the end of the semester, we will come back and deal with those in quite a bit more detail. My share screen didn't reactivate. There. All right. If you look in your textbook, you will see some pictures at various points in the chapters that talk about space filling models. Some of them will refer to as the ball and stick models. We might have an opportunity at the very end of the semester to spend a few minutes in lab dealing with the actual Tinker Toys. I have a set of Tinker Toys that I usually show that I bought specifically for Zooming with, so that you can kind of see what some of those things actually look like. But that will kind of circle back to that later. So the last little chunk of information that we want to deal with tonight has to do with the way the periodic table is arranged. Okay. We see it as something that kind of has a profile that looks a bit like this. Okay, it has these kind of like staircase, and then it goes down here. Actually, I put one too many stairs in there. Kind of goes like this and this, and then it goes across, and then up here, and back across. Okay, and there's a couple of stripes that go across the bottom here. So when you look at the periodic table in your textbook, or you look at the one that's loaded as a file, this is kind of the shape of what you see. Going across, there are rows referred to as periods, hence why it's called a periodic table. There are 7 periods. Okay, if you actually count the rows, because the ones at the bottom are actually not separate rows. They have little indications that go insert here. Okay, if you actually spread the periodic table out to fully embrace the fact that there are 7 periods, it is very, very, very wide, which is why they clip out 2 pieces of it and usually put those 2 stripes at the bottom. You will also see that the vertical columns are an organizing factor. They are known as groups. I am going to focus on the version of the periodic table that labels them with Roman numerals, as opposed to the version which labels them 1 through 18. I find that although it gives you information on one facet of the way the periodic table is designed, it is also very deceptive because it misleads you in many ways about how some of these elements behave. So we're going to focus on the Roman numeral method for how the table is labeled. I'm looking at my lab book, which unfortunately is in black and white. All right, so if you look at the back of your lab book here, you'll see these 2 columns are Roman numeraled with A's. All of these in the middle are also Roman numeraled with B's, then you have more A's going across this way, okay? We're gonna focus on this particular naming method or labeling method as opposed to the regular number values, the not Roman numerals, the Arabic numbers, as we sort of begin to organize how the table is put together. All right, so we have finished chapter 1. You should see when you log into Canvas that your homework for chapter 1 is due tonight at midnight. A few people have handed it in already, and somebody asked me earlier if I had started grading them, and no, I haven't. I won't start grading them until tomorrow morning. So you definitely have all the way through till midnight to turn them in. We have now done about a little less than half of chapter 2. Some of you I will see in lab tomorrow night. Like I said, if you have a lab book, great, amazing, bring it. If you don't have a lab book yet, you really kind of got to get one between now and next week. But all the dry lab stuff is loaded. Some of the experiment 1 stuff, both of which we're going to be doing parts of, both dry lab 1 and experiment 1, they're going to do parts of both tomorrow in lab because it's summertime and we're still stuck with this dumb rotation thing. I will see if I can get some additional photocopies of the report sheet for experiment 1 to bring with me, but definitely if you have your lab book, bring it with you because it will make life much easier because we are going to be doing a lot of data gathering and actual wet chem lab stuff tomorrow in lab. And then once tomorrow's lab is done, then we actually sort of return back to a more normal schedule, at least until the 4th of July, where A group and B group actually happen in the same week, okay? It's actually instead of being spread 2 weeks apart. So at least things will kind of get a little bit more streamlined. Another thing that's true, especially for people who have not had lab yet, you might have noticed that if you choose and you are vaccinated, you do not have to wear your mask to lab. Safety goggles, yes. The mask is now your choice. If you feel more comfortable wearing it, or you haven't been vaccinated, or you have health issues, obviously feel free to wear them. But you are not required to wear them in lab now, which does make certain things easier. There was something else I was going to say about lab. Oh, I am usually on campus at least 30 to 40 minutes prior to when lab starts at 4 o'clock. So feel free to take advantage of that as treating it as office hours. So if you are coming to lab anyway and you have time to come early, you can ask me questions. It could be about lab or lecture. We also, I thought that there was a lab that occurred 1 hour after mine. And in fact, actually, that's not true. The other lab for 111 that occurs in the evenings is actually on Tuesday and Thursday. So if you need some extra help and you want to hang around a little bit after your lab, you can also utilize that as office hours time to ask me questions about, like I said, lecture or lab. It doesn't matter which one. Questions? Some of you I will see tomorrow night. I'm not entirely sure what's going on about the whole Zoom thing. I'm probably going to just start pasting them in the announcement section because it seems like it's giving me different numbers on different days, which has caused much confusion. I hate Zoom. And some of you I will see tomorrow night.
All right, thank you. Have a good night.
Thank you, Professor. Have a good one.